Welcome everyone to today's webinar. My name is Dan Hooper with ISI in Dallas, Texas. We're the parent company of SQLRX. And by way of introduction, SQLRX is all about optimizing SQL Server performance and capacity. Our presenter today is a subject matter expert, Jeff Schwartz, and he'll be taking over in just a minute. I want to give you a quick overview of SQLRX and how it differentiates itself from the common tools in the marketplace that attempt to analyze and debug SQL environments. SQLRX is different in two primary ways. Firstly, there is no software to purchase or download. It is a software as a service, and we'll give you a couple of opportunities to assess SQLRX if you have not used our tool at the end of the presentation today. The second way that SQLRX is quite different is in the output, in that SQLRX will identify specific root causes as to performance bottlenecks or capacity constraints or issues that are generally diagnosed at a symptomatic level with the common tools, leaving you to go find those root causes. Our output will specifically identify those root causes and the steps required to resolve them. So with that said, I'm happy to turn over the presentation. There's a lot of material here today, but very informative on must-haves for optimal architecture and performance. So Jeff, it's all yours.
Thank you, Dan. Today I'd like to discuss some guidelines about handling SQL Server performance and applications and queries. So just general topics regarding that. So application developers are often under pressure to get functionality out the door by a certain deadline, and a lot of times because of that, the scalability and the performance, sometimes short-term even, suffer because of this, but quite often long-term. And they frequently believe that they don't have the time to test performance. They just have time to get the functionality working and get it out the door. And there's nothing else that they can do. They don't have the time. And small databases, to that end, small databases are often used for all testing, including performance testing and shaking everything out and making sure it all works. And my contention is that developers can do both. They can create functionality while making sure that their application is understood from a performance perspective, but also have the ability to later on, should performance problems arise, they have the ability to go ahead and figure out where they are happening and what to do about them. So small databases, they're appropriate for initial development. However, some people use them exclusively for every bit of testing there is. And the problem is that all queries perform well when a database is small enough, regardless of whether they're designed well. You could have 35 joins in a query, for example, and if the records all have 100 tables all have 100 records in them, you're fine. It won't matter. The other thing is SQL Server, if they're small enough, will use linear searches to get through all the data anyway. So you can't even really see what the plan is that SQL would use when you had 10 million records, for example. Indices for in these situations are often figured out hypothetically. It's based on what the usage patterns they think might be. Well, I think this rule is going to be used more than that rule, those kinds of things. So many times those, unfortunately, do not align with SQL Server's optimizer's choices of how it's going to attack different problems, especially after the database has gotten to be a certain size. And the other problem we have is that growth levels are often unknown or difficult to determine because, for one thing, even a simple one like record deletion routines, a lot of times those are not written until the database has gotten so big that it's mandatory. And that's just one example. Another example is that tables that were envisioned to be very small have suddenly become very large. Just maybe a regulation change, business change, something like that. One of the other reasons for doing some of the small testing is that hardware availability may not be that great. You may have a little desktop, a laptop, or something like that that just can't really on it, or you're in a VM or a shared development server where it has limited resources. Excuse me. In short, everything performs well under these conditions, and it does not give you a good indicator of what's going to happen in the future. So first of all, don't assume that queries are going to scale. Typically, what I see happen is people write queries that work well for small data sets, and they fall over and can't get out of their own way when they get to be dealing with large ones. You have to plan for data growth. Now, since disk space is inexpensive, even though it may be sometimes difficult to obtain, it's really important to create at least one big sample test database that has a lot of records in it, even if they're fake. And then, even if the space is truly at a premium, back it up, archive it off until you need it again for some kind of performance testing. But at least have one around that you can load it out and take care of it and run it through its paces. And then, even if the hardware is not very strong, you still can get a lot of mileage out of this kind of testing. So first of all, measurements. Some measurements are going to be good in absolute terms, other times in relative terms. And some are going to be more valuable than others depending on the environment. So for example, CPU time is useful as a relative measurement unless you're running on a VM guest whose host is overloaded. And by many people's accounts, a host that is over 50% busy is going to have trouble servicing all the guests in a timely manner. What this does is it skews any kind of time measurement. And when that happens, you can't count on time-related things. Duration is not very useful except as a relative measurement. On a dedicated server, it's actually perfect as a relative measurement. It's not that it's representative of what will happen in production, but it is representative comparative to some other difference, some other change you make in the application or the code. It's less useful in a shared server or VM environment because so many other things can affect your elapsed time, and so consequently, that's not a very good number in those situations. So it depends on what environment you're running in with your big test database. However, logical numbers and row counts are going to be accurate no matter what the environment is. So no matter how much memory is assigned to SQL, no matter what any of those other things, your logical work will remain the same. If you're going to read the database 400 times, you will read the database 400 times, whether it's got a lot of memory, a lot of CPU, good I/O or not. The physical reads will change because of the memory situation, but logical reads will not. Excuse me. So developers can create the functionality for understanding and preparing for performance right from the beginning. I believe this should be done for native application code as well as stored procedures. It's a lot easier to do it when you're building it than when you do it later on, trying to shoehorn it in and figure out all the places you need to stick a timer. It's very difficult to do. Quite often the people that have worked on the code originally are gone and on to other projects. So it's very difficult to go back and find all the places that need to be caught. So it's also very simple to instrument the code for performance, and then you can just start and stop it as needed, include it or exclude it as needed, whatever works. You can also write these to an application log file. I've even seen this done with online programs where the response times will be written to a log file so you can see exactly what the responses were. Now, maybe you don't do this all the time, but there'll be a flag that you can turn on that would activate this kind of stuff and find out what's really going on from the application side. Compile time options are very useful for this kind of activity. So, for example, let's say you have a piece of code that does a lot of work and it's got a lot of classes, modules, and whatnot, a lot of procedures, and all things are run all over the place. You can have a very difficult calling sequence, and you don't exactly know where your problem is. You just know it's taking a long time between X and Y. When you have these kinds of things, when you're building it, if you know that these areas are prone to difficulty, what you can do is actually instrument them so that when you need them, you can just include it. And then you know if you turn on a flag, like a compile time flag, and the code is included in all the different places that it needs to be included for that kind of timing. have many different compile time options. It can be as fluid as you wish. It's most useful, obviously, in a test environment to reproduce this problem, but I have seen cases where we've had to slide in that kind of application into a production environment to really catch this thing in the act. So when you're doing this, you want to instrument the code during construction. You have two choices. You want to have a compile time flag or a runtime flag, and you can use a combination of both. So time recording, whether you record the time or not, can also be controlled by flags. So you can have this flag on when you can record the time. Otherwise, you could just say, well, I'm going to record, I'll compute them, but I'm not going to write them anywhere. But they're there. And this is kind of what the Windows operating system and SQL Server database management server do. The timings are always there. Whether you go and reach in and grab them is up to you. But they're always computed very cheaply. And I'm not talking about adding a lot of code here. I'm not talking about adding a lot of delays either. They're very quick calls. High precision timers are recommended, especially for high frequency types of visiting code blocks. Precision is down to the clock tick. You can use it with any language that can access the Windows APIs, and I've got some examples coming up. If you're using .NET, datetime.now is accurate within about 10 milliseconds. So again, if you're looking for the big ones that take 30 seconds, that's fine. But if you just have a general slowdown, 10,000 transactions are just taking too long, where are they spending their time? This kind of timing can be very appropriate and give you a very good indication about what's going on. It isn't always in the database, or it may be a database call you're making. For example, I helped a customer once where they made an application call to a library, and it was the library call that took 30 seconds to come back. And they didn't know that until they actually turned on the timers. So here are the functions you want to use. This is how you declare them. This is in Visual Basic, but you can modify this easily for C# or any other language you wish. Basically, you have a function that grabs the time, a function that does the difference, and a function that actually computes the frequency of the processor, so the numbers will all make sense, because otherwise the numbers won't make any sense to you. And then the final one actually just takes the timestamps, converts them into a time that you can understand. And as you see, I've got some decimals there. You can add as many decimals as you want. This is the invocation. These are compile time options. So I've got, if I set the compile time flag BLNC obtain timings, I initialize the timers. I get my first time. I do some work. I turn the timer off, and then I do the diff. That's basically all that happens. So you can put these anywhere you want, and you can combine them with runtime flags, obviously, and it makes it very simple to do. Here's an example of C# doing a similar kind of thing. If you look at the two yellow highlighting blocks, if I have that turned on where it says BLNC return parsing time, it will actually return declare a variable, and then it does some work, and at the end, it'll return, instead of what it normally would return, it will return the time. So this is actually in a CLR routine that I have for SQL Server. So this kind of thing can help you out, and it's very useful to time blocks and say how long. In this case, I was doing some regex kinds of search patterns, and I was trying to see it. The queries I was searching were very long, and I was trying to see how long it took to actually perform that kind of regex searching. So it can be useful for database calls, non-database calls, anything you happen to be doing. So for T-SQL, there's basically three main choices. You roll your own. With date-time variables, you have a 3.3 millisecond accuracy. You can get better down to 100 nanoseconds if you use time, if you have access to SQL 2008 or higher. Statistics time provides information about the compilation and execution times. Statistics I/O provides information about reads and writes, both physical and logical. You can also, the third option is to capture statement and completion events either with SQL Trace or with extended events if you have access to 2008 and higher. The statistics I/O and time generate output for each statement within a batch or stored procedure. So for large batches, stored procedures, or complex calling sequences, it gets to be very difficult to figure out what numbers go with what query. Because it doesn't print the query, it just prints a bunch of numbers, a bunch of timings, and I'll show you those in the next slide. The problem is you have so many of those, you have to start counting. Is it this 10th one, and how did I get to the 10th one, and all that. So sometimes I find it a lot of times easier to do my own, and unless I just have a single statement I'm working on, and then either using trace or X events, which is what's short for extended events. And that means I can actually sort things. I can do all kinds of, I can say, okay, I executed 30 queries. Which ones were the bad ones? And in what way were they bad? X events has changed substantially from its initial release in 2008. Each release gets more powerful. On 2012, they implemented a wizard that makes life a lot easier to try to use these things. The capabilities are actually growing tremendously, too. On 2014, I think it is, they added the ability to get the actual query plan out. So if you have a misbehaving query, you can actually get the plan dumped. You obviously wouldn't want to put this in production, or at least in a very sparing manner, but it's nice to be able to have that access to you. Print statements. A lot of people use print statements to do these timings. The problem is they leave them in after they are done and they are in production. Print statements actually create network traffic, so they create a lot of overhead. We have actually seen cases that are definitely measurable improvements by just turning off all print statements that were hiding in stored procedures in 2 or 3 of them. So you don't want to add to this problem. So again, if you're going to use print statements, control it with a flag. It's an optional flag, and then you don't have to worry about it. You turn the flag on, it gets invoked, otherwise it gets skipped. Here's what statistics time look like. This is all you get. So you don't get the query you went with, you don't get anything. So imagine if you had 30 of these, it would be difficult to figure out which one was which. Obviously, the last part of it was the worst, but it gets to be tough to figure out. But it does give you the CPU and the elapsed time. So again, for a single query, it can be very helpful. Statistics I/O, I usually use these in concert when I'm using them, because it tells me how many logical reads, physical reads, read-aheads, all kinds of other really good information that I really don't get elsewhere. And so it's very good to be able to look at all of these together and figure out what you're going to do. So this script, I provided it just for the sake of completeness and to give you an example. This one will act if you do a SQL trace, and you can see I catch it from different systems. What it does is it reads the trace directly. I left the commented stuff in there deliberately so you could see all kinds of variations on a theme to see how you might use this. It's very handy. Instead of trying to use Profiler to look at it, you can just go in and query the trace directly. You don't need to load it in the database. It's very easy to use. Extended events. This is the one that I've been using more and more. This is from an SSMS. The only right way, there are ways to look at it through a query, but the easiest way right now is to look at it through SSMS. And you can see an example here of statement completed. It shows you what time, and then you can see all the information you get from it, duration, all those kinds of things. So those are certainly good options to use. Join ordering is the order in which the joins are performed can be very important. Most people just add the joins to get it to work, but they can make a big difference in terms of performance, especially when you have a bunch of little tables and some really big tables, and you want to be able to figure out what's going on. So what we used to do is to do physical ordering of the joins, and that would hopefully get SQL to cooperate. These entities called Common Table Expressions, or CTEs, which I'll discuss more in a little bit, those are going to help enforce that join ordering because SQL Server often honors it, and it seems to vary from release to release how much it honors it. And we'll talk more about that shortly. The thing I'm noticing, though, is that large tables seem to throw this kind of ordering, even with CTEs, more than it used to. In 2005, it was pretty clean. 2008, it did it less, and 12 and 14 seem to do it even a little bit less. But it's still useful, and there's other things we'll talk about shortly that will help you. So you want to use query plans to identify statements to, when you have bad statements, bad queries, you want to figure out what parts of them are bad. A lot of people don't know how to read query plans well. They don't feel comfortable doing them. And you want to find out the resource-intensive operators, the number of rows, the average size of a row, to figure out what's going on and which ones are the bad parts. It gives you some. It may give you some opportunities for new and revised indices, and sometimes they'll actually come up with a missing index. Sometimes you have to deduce that you could put an index on there and it would help it. It all depends. But join ordering issues really can hurt you because quite often the physical join order now is no longer equal to the actual join order. So if you have 15 joins, you need to be very careful about when they get invoked and what kind of result set you end up. If you take, for example, the first join you did is creating this mammoth 400 million record table that you're going to then whittle down later on with joins, that creates problems. Whereas if you do it the other way around and try to build up all the joins and then touch the big table at the end, that quite often works a lot better because you're not dragging this big table around with you as you try to do every other join. And it's as simple as that. So you want to revise the statements or the database schema, depending. But common table expressions came out on 2005, and they give you a better chance at improving this ordering so that you can actually have some control over it. And the main thing is that the big thing from a developer's point of view is that you can build the queries gradually. So you can add this join, add the next join, add the next join. When does your query go from performing well with a large data set to performing poorly? I've seen cases where I can add 9 joins, the 10th one is the kicker. But it's very helpful to know which join it is that's going to kill you. And by doing this method, you quite often can eliminate the need for temp tables or the explicit kind, the kind you declare and use. But you can also minimize their usage. There are times when I've had big queries that don't work exactly as I plan, and I've had to resort to a temp table as the last step. But it's not that common, and this kind of rearrangement can result. I have one query that was running 2.5 hours, and I dropped it to 5 minutes. That's how important this can be. So execution plans, query plans, they're both synonymous. There's a diagram. That's the visual one most people are familiar with. There's textual and XML representations of both of those, and basically it's how SQL is going to accomplish the query. There are 2 kinds. There's estimated and there's actual. There are 3 types. There's graphical, textual, and XML. I tend to use the actual whenever possible, and I use the graphical quite a bit, and now I'm starting to use XML more. They each have their benefits depending on what you're trying to do. Sometimes it's easier to see the effect of embedded loops with XML. It's a lot easier to see that in the XML kind versus the diagram, the pictorial kind. So loops and joins and statistics all have very great influences on performance. If you run the actual plan, it can slow your work down a little bit. Views appear as part of a full query. So here's the thing. When you have a query that does a lot of work and it's based on a view that also does a lot of work, all of it shows up in the query plan as one big mess. And it's hard to say which part of this is coming from the view and which part of this is coming from the query that uses the view. And so you have to be very cognizant of what's going on. So a lot of times what I do is get the query plan for the view, and then I get the query plan for the two together and see what's different. A lot of times you'll get missing index notifications in the query plans. Index recommendations never occur for a full index or table scan. So if you think you are going to be able to get away with having, like, okay, I'm doing a full scan. SQL, please tell me what will make this not a full scan. That doesn't happen. It just drops into full scan mode, and that's all you see. There are no recommendations. There are no missing indices, anything. It's just that only happens for other types of queries, but not full scans. Also, the recommendations are dependent upon the items in the queries, so you need to be able to understand that one recommendation that has A, B, C, D in it may have the same recommendation only for another query that does A, B, C, D, E. There'll be one recommendation for A, B, C, D, one recommendation for A, B, C, D, E. And so you have to kind of figure those out and figure out what to do. So basically, try to eliminate full scans as well as any kind of read or key lookups. I'm going to go over this quickly. I mainly did it here for the sake of being complete. Graphical query plans are where most people begin. Each node, each operator is an icon, and you can then, they're connected to other nodes, and then you have the number of rows that come out and number of rows going in, all that kind of thing. The arrow width is proportionate to the number of rows, so you can kind of look for the fatter ones first. However, the fatter ones aren't always the best indicator, excuse me, because the loops tend to have one row operated on at a time, and the loop will actually, but the loop will be executed for every record in a table. And so consequently, the loop could be executed 10 million times, but each one of those operators for that loop is really cheap, but the collective effect of the 10 million is terrible. So when you have multiple statements, you have multiple query plans, and for parallel queries, if you see the little beige circle with the two little arrows, that is that means a parallelized operator. That means that it can be very expensive. It can be a real killer. It's the one that will start to take over machines, and it's the one where when you have the experience of queries just dominating machines, or you have to put a governor on it or whatever, it's these kinds of queries that you're trying to govern. So if you see this in a query, you know you're doing a lot of work, and you may not be able to get away from doing a lot of work, but anything you can do to improve it would be better. The most common operators you're going to be dealing with are clustered index seek and non-clustered seek, RID lookup, key lookup, scans. And the last, any kind of scan is usually bad. That's kind of the deal. So nested loops, again, I just mentioned they're very deceptive. They are. You can look at, like, well, I'm only looking at one record, it's great. But then when you look at the collective effect, it's millions, and that's the problem. When you see bitmap operators, you're in trouble because it's actually having to mash two things together. Hash match is just as bad or worse. And so what it's saying is you've got these two massive tables, and you've got to mush them together and create a third table, and then you work from that third table, and that's very slow. These are operators here, because this is kind of an overview class, but I want to give you some information to work with. Merge joins, anytime you see a spool, anytime you see streams, parallelism, those are all signals to you that you're potentially in trouble with that kind of operator, and it could be causing a lot of problems performance-wise. So an efficient query plan looks like this. It's got a seek and a key lookup. There is a way to improve this even, but for now, this is an efficient one. You can see it pulls back. You can see the thinness of the arrows. I can't hover over it and show you, but it's only a few rows, and it works great. So the table had almost 21 million rows in it. This query returned 243, and you can see the work it required to actually do this. And this I got from statistics time and I/O. So again, I was working on a very specific query. Here's an inefficient one. Here's one where it just plowed through the table. You can see the index scan. You can see it parallelized it. If you go back here, you can see there's no parallelism. Here there is parallelism, and you know it's going to take a lot of the processors. Excuse me. It's going to take a lot of the processors to actually do this query. It's going to just hum. So here you can see you did 1.9 million reads logically. Most of them were read ahead because it was plowing. It took 21 seconds. The other one took 21,000. This one took 16. Elapsed time was basically 5 minutes. Yeah, 5 minutes, and this one took, the efficient one took 2 seconds. So here's the comparison in a table, and you can see that it saved almost 22 seconds of CPU time, and if you ran this query 100 times, you'd save 36 minutes of CPU. Plus, you'd reduce a lot of pressure. So you can see how this kind of thing can work. To my point earlier about using small databases, sometimes you will have small databases that would be table scanned, that small heap with the red arrow. That is what always will happen with a very small plan. Everything will be a table scan or a clustered index scan, and there's no way around it. It's just how it's going to be. The key lookup is something we want to get rid of, and that would be addressed by the missing index, clustered missing index recommendation. And that's how it appears in a query plan. But again, as a reminder, you will not see it for any full scan kinds of activities. So what do you, excuse me, what do you do about views on 2005? Non-indexed views are basically a query, that's it. So here's a scenario that I've seen time and again, where you have a query where some column of that query equals 5, works fine. You change the query to a view, and then you say view where column equals 5 performs terribly. Why? And invariably, this will happen in production when the database finally grows big enough, and suddenly there's a big mess. Well, when complex queries, starting with 5, and it's been getting more pronounced ever since, so it is the way of the future. A big view quite often is materialized before. So if you have a massive view, you will create a temporary copy of the massive view in a work table, and then you will actually start to apply the 5. And that's generally not what people are thinking. I have seen exceptions to this, where some people actually, sometimes the query optimizer will be smart enough to see, okay, if I get rid of all this other stuff, I can just end up with what I need. But sometimes when you have enough joins, I've seen cases where there's 13 joins, SQL can't figure out which path to use that isn't going to eliminate any table usage. So instead of having the monster view of all time that's going to take care of everybody's problem, try to make very tailored views that actually bring back only what people need under certain conditions. And maybe sometimes they need the monster, but not all the time. So are views obsolete? Not necessarily. It depends on how many, depends on what kind of joins they use. It depends on whether or not the view by itself is all right. If not, you might want to rewrite the view using a common table expression, or tailor the view so that it's used specifically in a very efficient manner for specific purposes, instead of trying to just make one view that's used by everybody for everything, because those days don't work anymore, especially with large tables. So I've referred to common table expressions a lot today. Common table expressions, here's the definition of them, which you can, with the purpose of it really is you could think of them as subqueries, but subqueries that you can do things with, almost like building blocks of a query. That's how I look at it. So you can make this query a little block and that query a little block, and then you can join them. and then you work your way down and build up your query that way. I find that, first of all, it's very readable code, and secondly, you can use recursion, parameterization, and things like that, but also it helps you as you build it. You add the last little piece, and boom, it causes trouble. So some rules of the road here. You want to do them incrementally, as I mentioned, to build your query. You want to find out exactly which joins are the ones hurting you. If I have 15 joins I have to do, I try to get as many of them done, and then I leave out the ones that I don't, as long as I can, and then I try to save them toward the end. That's basically what we're doing here. The key is you want to filter out as many records as you can as early as possible. So if, in fact, your biggest table can be filtered down to 200 records right away, then do that and then start working from there and building on the joins from there. Sometimes you have to do it the other way around, where you add the big table last after everything's been figured out. It just depends, but you have to play with it and see which way works. So here's an example of actual CTEs. You can have CTE1, CTE2 can select from CTE1, and then you can join other tables. This is the most common example you'll see in the books. The ones you don't see very often are number 2, where you see CTE1, CTE2, and they join the 2. That's the one I use a lot. I'll use a combination, basically, of the first 2 items. So you can be very creative when it comes to CTEs. The only thing you have to remember is that you have to, just by it being existing in a query doesn't mean that it can be recognized by the subsequent items. You'll have to either from it or join it in some way. So the way to build a query the best in using CTEs, you want to construct your innermost query and create the smallest, narrowest result set you can. Put all your where clauses right up front if you can, and then select star from CTE1. Just make sure what are you getting back? Are you getting back what you're supposed to? Check the query plan. Make sure you're getting what you're supposed to get. The select star doesn't mean bring back everything from the table. It means bring back everything from CTE1, and it allows you to see what CTE1 is going to do and how it's going to work. And then you do the same thing for CTE2. And you keep working that way, looking at statistics, possibly tracing, X events, whatever. And you keep doing this, keeping your result set as small and as narrow. By narrow, I mean instead of having a 600 KB record width, you have a 10 KB or 5 KB or a 100 byte record. Make it as narrow as you can, because a lot of times the bigger it is, the more likely it's going to end up in TempDB, and then you end up with disk involvement, and again, it slows it down. So basically, the upshot is you want to continue the process, keeping the result set as small and as narrow as possible, as long as possible. Save joins until the very end, especially with outer joins, because those tend to mushroom the result set very quickly. And then you want to add them one by one. There are lots of times when I have some very difficult joining a lot of really big tables. I will do one join per CTE to make sure that I'm not going to introduce terrible problems. So most often I can get away with the entire query being in a CTE. Sometimes there is one query, one join that will actually throw the entire query. So you have this beautiful plan, everything's efficient, and the next thing you know is you add this final join and it throws the plan and you can't even recognize it anymore. So at that point you know that SQL has become confused, and in that case what I do is I will take all the results up to that point, I will drop them into a temp table, I will then take that last join against the temp table, and it works beautifully. It's very quick. It's not ideal, certainly not from a maintenance point of view, but it works very well. So the kinds of joins you want to worry about are outer joins, cross apply. Those are the real ones to worry about. And outer joins means left and right join. Inner joins can be bad depending on if you're trying to interjoin with millions of records. So indexing. You want to index tables with growth in mind. You want to use query plans, and that's why I covered query plans, to figure out which ones you're accessing, how you're accessing them, and what you want to do about it. What should be indexed, what's important. Don't guess and hope. I see that a lot. I had one customer had 144 indices on a table. They were just trying to hope that some combination would work. And that actually worked against them. So the query plans will tell you how your existing indices are working. So for example, you're building a query. You have a nice index that you think is perfect for that query. You look at the query plan and you find out the index isn't used at all. Then you have to figure out why. And that's really important. So why have an index that isn't going to be used, even though you think it ought to be used? SQL's choosing not to, and you have to reconcile those differences. Again, as I mentioned before, you want to look at the missing index recommendation and take it with a grain of salt. There may be 40 others that look just like it, with slight variations based on the number of items, number of columns brought back from the query, so from the table. So you have to just look at all of them, not look at one or two and say, oh, this is covering it. And also, I didn't point out, I'll point out in a minute, there is an impact number that's estimated, so you can use that as well sometimes. So don't over-index. Don't give the optimizer too many choices. What happens is the more choices you have, that becomes exponential, and you can't figure out all the things you have to do. So what happens is the optimizer says, I have a certain amount of time to get this query figured out and develop the plan. Once I do that, I have to be able to, I can only dedicate, say, 2 seconds to it, let's say. And so whatever it can do in 2 seconds, well, if it has 144 indices from which to choose, it'll only get partway through that process before the time expires, and it just takes the best one it's found so far. And so therefore, you want to under-index if you can, and just be very judicious. A lot of times with customers, I will trade indices. I will take one that's hardly used and move a new one in that's going to be used heavily. So, and not to mention, if you do massive insertions, which I have a lot of customers that do that, it can kill in performance. So just going back over the plans we had, this is a query plan with an index seek and a key lookup. So we would, if this were a really heavily used query, we'd probably try to get rid of the key lookup, but it's still an efficient plan. This one is a plan with an index scan. These are the same plans I showed you before, but I wanted to summarize them in this manner because this is where you can find it easily that this one is the one that had the index scan on it and the parallelism. The query with the plan with the missing index is right here, and you can see the impact in parentheses, 92.7231. That gives you, and if you can actually right-click on that missing index, and it will give you the full definition of what it thinks the index ought to be, and go from there. And if you're not familiar with included columns are ways to have information come along for the ride but not be actually part of the index tree structure. They're in there at the lowest levels, but in the higher levels of the binary tree, they will not be present. So in conclusion, you want to use large databases for at least some performance testing. Even if it's fake data, you need to do something to figure out what you should be indexing. Is your query going to work when it's 10 or 100,000 records instead of 500 records? Instrumenting code from the beginning, you saw how simple it was. You could just add a couple of little flags, a couple of include a couple snippets of code, and away you go. The logging I didn't show you, but the logging, you can take those numbers and just write them down. That's what I do. And you can, I cannot emphasize enough using query plans to figure out what's going on, how to make your stuff work better, and what indices you're actually using. But again, please remember that with a tiny data set, you this will be not as valuable as it will be with a big data set. And as you're building your queries, try to use them with CTEs when it's appropriate. If you have a very complex query with a lot of joins in it, and you're mashing a lot of things together, I tend to do all of it in CTE form no matter what, because it's a lot easier to keep it straight when you build it. It's a lot easier to figure it out when it breaks. And at that point, thank you for listening.
Jeff, thank you very much. As we mentioned at the top of the presentation, we'd like to give you all that have attended a chance to check out SQLRX. Our health check is a free offering, so just note Jeff's email or my email, and feel free to call us or email us if you're interested in that, in addition to our assessment analysis and an ongoing monitoring tool known as Remote DBA. There will be a posting for all that registered of this presentation with a link and its recording, so feel free to send that on to those that couldn't join today. And as well, if you'd like a copy of the presentation, let us know, and we'll be glad to get that to you. So that concludes our presentation. Thanks for attending. Please take a moment to